he will go in depth with new emergent technologies and how it can be a building blocks for our stories at the hackathon. When I first had a communication with Ache, he sent me a mail yesterday evening and he said, I will try to quote, but I will not manage to. He said, like I read, best speakers sleep 9 to 10 hours or 8 to 9 hours before a speech. I did not, but I think he did. So let's see how it makes a difference on stage. Please welcome Age van Der Mei.
Thanks, Max. You're giving our secret away. Hi, everybody. My name is Age van Der Mei. Glad to be here and see you all. I have the enjoyment and the pleasure to go with you to the deep dive. This is my request, and I had a lot of fun in preparing for this deep dive. Because normally you're asked to speak about the story, but I will here really endeavor to see if I can assist and think with you towards the 5th and 8th of April. And if anything is unclear, please let me know and see me during the breaks or after the session. So let's start. Machine ecosystems. What is this all about? Inspiration by nature. I love this from the last talks. How could we make this concrete? How could we code on this? How could we design this? How could we use the blockchain to get this out there distributed? Big questions. And this is something I've been thinking about over the last weeks when I got this request. And it's important. Because why is it important? Because it might assist and help us in, well, solving some of these big issues that we have. And I want to start with this image. It's Earthrise, and normally you see it from the moon. And it's the image that was the start of the environmental movement in the 60s. So they were standing on the moon, and they took the first image from the moon towards Earth. And they saw something that looked like this. And it was this redefining, this reimagining of what we are doing and where we are and who we are. Now let's go through, fast forward, about how these new developments could aid us in these big issues, these topics of today, that I think we might be able to get our heads around. And my chief mission is to work on this. We're looking at Antarctica. This is, well, I would say, our big location where climate change will play out. Because if just this bit on the lower left, that's Wilkinson Bay, if that melts down, that part by itself will entail 6 meters of sea level rising. This is already starting to decay, the first bits of this big ice shelf. This is one of the big problems to work on. So we set ourselves the goal to work with a small dedicated team to help assist in reducing 1 megaton of CO2 by 2023. So I'm here on a mission. And why is this a problem? Of course, you hear about this quite a lot. But it's not really a problem. It's a choice. Because we got here because of what we have been doing. And now we're getting into the future because of the choices we're making today. And the big choices are, roughly, the 2 lines we see. The red line is business as usual, and the green line is the Paris Accord, more or less. They're remodeling the climate emissions. This is the choice we have. And then, about this choice, what would it require? Well, some of these people could help us into reimagining what would be required to make this choice. Could someone, well, give a hint or give a suggestion of what these people have in common? They're all dead. They're all men. A lot of them are bald. But did someone have a suggestion?
Yeah, they all have wild ideas. They were outcasts in their time.
I think Aristotle was pretty prominent, and also even Newton. Copernicus was definitely an outcast. Franklin, yeah. The key thing, thanks, is that they all caused a paradigm shift. And why is this relevant today? Well, a paradigm shift can be very useful to use as a concept together. Because a paradigm means the way you are viewing the world, other people, and yourself. It's part of the paradigm. So a paradigm is a crucial item in perceiving. And correctly perceiving is a crucial step into trying to solve all the problems we are faced with. So there are two shifts for a paradigm to be successful, and I would like to share them with you, because maybe somewhere in April we'll meet, and then we can talk about this. And then I'll ask you, have you thought about shifting the paradigm? Do you have a way to change this redefining of what we're trying to achieve? And what we set out to do is a few years ago, we looked at what is coming at us, just perceiving this future that is coming towards us. And we looked at technologies, emergent and novel technologies, and we looked in total, we were able to identify 300 new technologies. And I'm going to share with you our results, but first the question. Who thinks blockchain is more valuable than machine learning? 1, 2, 3, 4, yeah? And who thinks the other way around? Who thinks machine learning is more valuable than blockchain? Slightly more. Some are indecisive. Okay. Okay. Great. Machine learning is, of course, the larger branch for artificial intelligence, which is part of machine learning. And what we did, we looked at all these technologies and we said, okay, can we specify what the values would be if they would be adopted on a majority level scale? You have the 5 steps of adaptation: innovators, early adopters, early majority, late majority, laggards. This is the classical S-curve which each new technology has to go through. And we said, okay, what is the potential global value of these new and novel technologies? And we were honestly interested in this question, because which technologies could be revolutionary on a grand, enormous scale, okay, which has an impact on wealth? And we used the substitution approach. You can ask me about this more, and you can read about it in the white paper. But this is what we came up with. And we see that actually blockchain will be very valuable. It's in there, you can see it. But artificial intelligence and genetics and nanoscale technologies are 3 of the key technologies that potential value-wise could be enormous, would be up there compared to all the other technologies. The most valuable is robotics. However, it's not there. It's not out of the labs. It's coming at us. And then, Age, why do you show us these technologies? Well, I hope, but also believe that for your activities within your groups and your teams for the hackathon towards April, maybe this might be useful. So maybe you go through the problem setting and through your story, and you think, hey, Age was talking about these new technologies. Could we make use of them? So what we did, me and the team as assistants, is we created a small list that said, okay, based on the problem you're facing over the coming weeks or maybe months, how could I use these new technologies? And we came up with a relatively simple list, I believe, by highlighting all the functionalities you could maybe require or you could search for with your team, and then connect them with the technologies that would fit with them. Because nanotechnology, yeah, it's very useful, but actually to what extent? Well, maybe here in your, and that's why it's called a deep dive today, maybe you will find this useful over the coming period. Then moving forward, and this presentation will be shared, so you can use it as a reference. There's more references in the end of the presentation. But let's dive a little bit deeper. Let's now have a look at these ecosystems. So let's expand this view and ask ourselves the questions, could ecosystems be useful for our track and our deep dive? I think the answer is yes, for very practical reasons. And the reasons is that an ecosystem is pretty successful in total in obtaining its objectives, whatever they might be. Because if you now look at a problem and you're faced with solving this problem, you will run into the problem of having to do a lot of computations. Our problem, we're working with the energy system of the future, and if you want to model actually the total energy grid, you're looking at millions of nodes of users, and that is a combinatorial explosion, meaning it's mathematically impossible to solve. That's what this square law of computation means. So computation is extremely useful. However, the key drawback, the key limitation is this law, which is very difficult to move around. Because as the difficulty, the complexity of the problem increases, or the amount of nodes, for example, people increases, the optimal, the best solution becomes impossible to calculate. Remember this as you move forward. Because here actually ecosystems take a very different approach than what we are doing. And what are we doing? We're actually doing this, and very successful. And let me mention the key example that we all can relate to and that we remember. That's Newton. Newton, his feat of the discovery of gravity is called the greatest generalization achieved by the human mind. Why was this so? I would endeavor to state that the main reason was because of its elegant simplification. So Newton said all the planets are point masses, and we only have to consider two at the same time. Because if you want to solve the solar system and all its trajectories in one go, it becomes an impossible computational problem. So this is what we tend to do. We take the large problem and we separate them into subsets, which we can solve computational-wise. But of course, what we want here is to see, hey, could machines and ecosystems take us beyond this level? Where could this go to if we take a different paradigm? And this was a real question we asked ourselves. So we first looked at small energy grids, then we looked at the national energy grid, being the Netherlands, and then we said, hey, could we actually look at the total world and solve this access to energy, as we heard about it before, and can we help and use artificial intelligence into doing this? And we worked on this very intensively with the team from across Europe, and this is what we came up with. We said, okay, let's learn from nature how she approaches this problem. Because nature has a very elegant way of reducing complexity to relatively simple rules. And nature is, well, evolving from the first bits and atoms and molecules and RNA and DNA into life, from life to brains, and etc. So, if we take this analogy of nature and its design paradigm, could we learn from a full ecosystem? And the answer might be yes, but I'm not sure about this. This is what I hope to learn from you guys, maybe in the coming months. What we found is the following. if you compare an ecosystem performance with, well, let's say a classical approach, you get roughly this comparison. And this is actually a classical comparison between a species that is opportunistic, so for example beetles or bacteria, versus a full-grown functioning ecosystem. And this I would really like to share with you. Why? Just as a remember, maybe notes when you're stuck in your thinking, that you can go through and think, hey, how can I design my ecosystem for the machines, and what principles could I use? And these principles, they result in pretty effective performance. Measuring by the elements of ecosystem performance, it's total organic matter, so total biomass. That's large in an ecosystem approach. It's stability, so resilience of the system. There we can learn a few things. It's entropy, so meaning efficiency. And the last one is information. And I'll come back to this one in the next step. So in these 60s, this birth of the environmental movement, Janine Benhuis wrote a very inspiring book. It's called Biomimicry, what we can learn from nature. And she wrote these lines. And they're still true. More practically, how could you then maybe try to apply this if you design your ecosystems or if you're doing the game from BlockChain DB? Well, these could be some of the guiding principles and guiding rules that you could apply. They are, pretty simply, life-friendly manufacturing processes, meaning low pressure and low temperature, or ambient temperature. It's structures that grant function, so not only the material grants function, but also structure. It's self-assembly. It's avoidance of interfaces, because that's usually where things go wrong or break down. So nature has very little interfaces. It's redundancy. Cyclic transformations, so there is no waste. Waste is, in fact, a resource for the other items in the system. And it has low flow rates of material and energy. And the last thing is nature is optimizing, but not maximizing its performance. Then let's move to the next step. Could we learn a bit more maybe from brains? So we looked at ecosystems. Now, what could brains maybe tell us how we could design and work with these machine ecosystems? Well, first of all, brains, of course, they exhibit the design patterns of nature. And here I'm sharing, I think, a very unique image. It's the firing of a large amount of neurons, real-life neurons, in how a brain actually functions. So we see the large right spindle cells, and this is an example of what is going on in a brain. There are 100 trillion connections that are firing when you are thinking about topics. Well, how could we maybe take this analogy of the brain, these design principles, and use it? And here we're getting to the computer. Because Turing said in the 50s, basically any process of reasoning can be simulated, meaning can be computed. And here we're making a leap. And we're making a leap into this future. And actually we're at the cusp of this situation, because neural networks are the artificial equivalent of the biological neurons. Meaning, we're now actually looking at the first steps of where you have neurons performing the same patterns as what our biological neurons are performing. And what are they mostly doing, you ask? Well, most of the activity in our brain is pattern recognition. That's it. That's the main activity that the brain is performing. And of course, here we've seen the enormous breakthroughs in neural networks and large artificial intelligence. So if nature and evolution is pretty successful in increasing complexity and order, then maybe these are steps how we are moving through these evolutionary momentum. And then how could I design this? Well, the fun thing is, all of these new, well, let's say programmable elements of artificial intelligence, they only consist of 4 items. And the 4 are the environment, the performance standard, the sensors, and the actuators, so what is performing the action. And the beauty of this is the environment is, of course, where you could have the ecosystem approach and think about how you could actually change these 4 elements to have a performance that you are looking for. Now let me wind up and round off with the following observation. We're actually exactly this we're trying to employ in this problem. So this is one of those hard problems, mathematically. This is classically unsolvable. And we're taking an intelligent agent approach. And actually, it's a multi-agent approach using neural networks. And this might be an avenue that you could explore for your ecosystem's machine-to-machine communications. What we have been doing, we've adapted the light map of NASA, which is, I think, a relatively good proxy for energy use at this moment. So where you have a lot of light, so the intensity level basically tells you how much energy is being used in that geographical area. We're here working with 500 by 500 meter grids, so you can imagine the amount of data that is coming from these NASA satellites. What we've done, we've thrown it to the AI that we built, and this is some of our first results. So we're using a multi-agent approach, so that consists of multiple rational agents, to actually construct, well, ecosystem-like solutions for how to supply the world optimized, so not maximized, but optimized for energy. This is how we're going about the whole approach and the system. This is what I really wanted to share with all of you. And maybe, I hope this helps in your deep diving and your preparations for April. And let me close off by saying, who is actually changing this paradigm in the end? Almost always, it's the young or the people new to the field who change the paradigm, not the ones who are inside the paradigm, because it's very difficult to see outside your paradigm once you are very much embedded in it. So my challenge for you would be, over the coming months, would you be able, or how would you be able, to redefine and reimagine your own paradigm? So when we meet up, expect this question from me, and I hope to see you all in April. Thank you very much.